Hello friends, welcome back to my YouTube channel. This is part number 16 of my discussion on adsorption. I will continue my discussion on stage-wise adsorption. Actually, I had planned to start the discussion on multistage countercurrent adsorption, but I thought I should have two more lectures on multistage cross-current operation, in which I will discuss the application of Freundlich adsorption isotherm to a typical multistage cross-current operation. So in my discussion, I am going to consider a two-stage cross-current adsorption operation, and then I will tell you how you can apply the Freundlich adsorption isotherm to this operation. So in this discussion, I will be deriving an equation which will help you to get the concentration, intermediate concentration in the liquid phase. So that is, let me just talk about it. So you have two stages in a two-stage cross-current operation. So you are admitting the feed solution to stage number 1. It is contacted with the adsorbent phase, which could be a fresh adsorbent or a recovered adsorbent phase. And then after a sufficient contact, or after contact for a sufficiently long time, the liquid solution will be coming out of it. The adsorbent phase will be coming out of stage number 1, and in stage number 2, the liquid solution, it will be contacted with new adsorbent phase, and finally you are going to get the liquid solution that comes out of stage 2 and adsorbent phase that comes out of stage number 2. So in this particular discussion, we are going to derive an equation to find out the intermediate concentration or concentration in the liquid phase that is coming out of stage number 1. So the feed solution will have concentration capital Y0. Then the liquid solution that comes out of stage 1, it will be having the concentration of solute. And what is that concentration? It is capital Y1. And out of stage number 2, the concentration will be capital Y2. I have talked about what what is capital Y. Capital Y is nothing but the weight fraction of solute on a solute-free basis. So I have discussed all this in detail in my previous video lectures. I am giving link to the playlist that has all my videos on adsorption. You please refer those videos. So the objective for this video lecture is to get an equation for finding out Y1. So let us get the equation. Let us start the discussion. To begin with, let us briefly know about multistage cross-current adsorption. I have discussed it in detail in my video lecture on multistage cross-current adsorption. Let me talk about it briefly over here. So a typical multistage cross-current adsorption, it is carried out in a multistage cross-current cascade. So what is done? The liquid solution, it is successively contacted with fresh adsorbent in multiple stages. So we are going to consider the task of removing solute from a liquid solution. And if it is a cross-current adsorption operation, then what is done? The liquid solution is successively contacted with fresh adsorbent in multiple stages. So you can carry out this operation in a batch-wise manner, or you can carry out it in a continuous manner. If you increase the number of stages in the cascade, what happens? The solute recovery is going to increase. The solute recovery also increases. So that is a good thing. But the bad thing is the cost of physically separating the liquid and solid phases, solid and liquid phases in each stage, it also increases with the number of stages. So the advantage is you are going to recover more solute, but the disadvantage is your cost is also going to increase. So we know if you are using in a batch operation, filter press is used for physical separation, and in a typical continuous operation, sedimentation tank is used for physical separation. So since the cost of physical separation will increase with the number of stages, it is not economical to have more than 2 stages in a typical cascade. It is not economical to have more than 2 stages in a typical cross current operation. And what is the reason for that? The reason is, if you use more than 2 stages, what is going to happen? The cost of physically separating the solid and liquid phases, it is going to increase. So in my discussion, I have considered a typical 2-stage cross current operation. Let us continue the discussion. Now let us talk about 2-stage cross current adsorption operation. So in our discussion, we are going to consider a feed solution, that is a binary solution of A and B, components A and B. A is the solute that is to be adsorbed. Only A is strongly adsorbed. In other words, we are going to neglect adsorption of B. Adsorption of B is neglected. So that's why B in this case is the unadsorbed substance. The adsorbent phase that is being used, it is not soluble in the feed solution. This is the important requirement. The adsorbent phase, it should not be soluble in the feed solution. If you are using fresh adsorbent, then it will not contain any solute on its surface. Solute in this case is E, the component E. If you are using a recovered adsorbent phase, then it will contain some solute on its surface. So in a 2-stage cross current operation, what is done? The feed solution, it is successively contacted with a fresh adsorbent phase in 2 stages. Now in my discussion, I am going to consider a recovered adsorbent phase in each stage. That is, the adsorbent phase that is admitted in each stage, it is a recovered adsorbent phase, and that is why it is going to contain little amount of solute in it. If you are using a fresh adsorbent, then it will not have any solute on its surface. Let us continue the discussion. So first, let us understand the operation with the help of a simple schematic diagram. So this is stage number 1. The feed solution is admitted to stage number 1. I will shortly talk about the notations that I have used. The feed solution, it is contacted with the adsorbent phase. The adsorbent phase is containing some solute in it, since it is a recovered adsorbent phase. Then the liquid solution that is coming out of stage number 1, it is sent to stage number 2. The adsorbent phase that is coming out of stage number 1, it is removed from the stage. Then in stage number 2, the liquid solution is contacted with the new adsorbent phase. And finally, after sufficiently long contact, the liquid solution will be coming out of stage number 2, and the adsorbent phase will be removed from stage number 2. So the 2-stage cross current operation, a typical 2-stage cross current operation, can be schematically represented in this way. So this is the adsorbent phase that is coming out of stage number 2. I will shortly talk about the notations that I have used in my discussion. Let us move ahead. Okay, now let us talk about the notations. So in this case, L0, L1, L2, these are total masses or total mass flow rates of liquid solution. That is A plus B. Masses of A and B, or mass flow rates of A and B. So total they will represent total masses if it is a batch operation, and they will represent total mass flow rates if it is a continuous operation. Then you have S01, S1, S02, S2. So these are total masses or total mass flow rates of the adsorbent phase. That is masses of solid adsorbent plus solute, or mass flow rates of solid adsorbent plus the solute E. Then you have LS, which is nothing but mass or mass flow rate of the unadsorbed component. In this case, it is component B in the liquid solution. And then SS1 and SS2, these are masses or mass flow rates of solid adsorbent in the adsorbent phase. So SS1 for stage number 1, SS2 for stage number 2. So out of solid adsorbent and solid adsorbent and solute, which forms the adsorbent phase, SS1 and SS2, it represents masses of solid adsorbent or mass flow rates of solid adsorbent, only the solid adsorbent. Masses if it is a batch operation, mass flow rates if it is a continuous operation. Then you have small y's, that is small y0, small y1, small y2. What are this? These are weight fractions of A in the liquid solutions. So these are weight fractions of A in various liquid streams. Then you have small x, small x0, small x1, small x2. What are this? These are weight fractions of A in the adsorbent phase. Then you have capital Y0, capital Y1, capital Y2. What are this? These are weight fractions of A on A free basis in the liquid solution. And finally, you have capital X0, capital X1, capital X2. What are this? These are weight fractions of A on A free basis in the adsorbent phase. So I have talked about what are this capital Y's and then capital X in my discussion, in my earlier discussions. I'm giving link to the entire playlist of my video lectures on adsorption in the description section. You please refer those videos. So briefly, let me tell you, capital Y is small y upon 1 minus y, and capital X is small x upon 1 minus x. So this is how capital Y and small y, and then capital X and capital small x, they are related with each other. Let us now for the first stage, we have the operating line. An equation for the operating line for first stage is capital Y1 minus capital Y0 divided by capital X1 minus capital X0, that is equal to minus SS1 upon LS. I have derived this equation in my discussion on multi-stage cross-current operation. You please refer that video. Then similarly for the second stage, the equation for the operating line is capital Y2 minus capital Y1 divided by capital X2 minus capital X0, that is equal to minus SS2 upon LS. So in this discussion, I am going to use those equations directly. I have derived these equations in my discussion on multi-stage cross-current operation. So over here, I am taking those equations in my discussion. Let us continue. Now, operating lines, how the operating lines are plotted on the equilibrium diagram, let us understand. So you have the equilibrium data, that is various values of x that are in equilibrium with various values of y. If you plot those values, you are going to get an equilibrium curve. And then on this, the diagram, which is then the equilibrium diagram, you can plot those operating lines. I have discussed it in detail in my video lecture on the cross-current operation, multi-stage cross-current operation. So for stage 1, for stage number 1, the operating line for stage number 1, it passes through 2 points. Which are these 2 points? You have x0, y0 and x1, y1. So we need to know these 2 points in order to plot the operating line for stage number 1. So first, we need to understand that the operating line is going to start at a point which has coordinates of x0 and y0. Let us know how to locate that point. So you are going to locate capital Y0, and then you are going to locate capital X0 on the x-axis, capital Y0 on the y-axis, capital X0 on the x-axis, and you get point P. Point P has coordinates of x0, y0. So this is the starting point for the operating line for first stage. And then if you look at stage number 1 and look at the leaving streams, if the leaving streams, leaving liquid stream and the solid stream, if they are in equilibrium with each other, if the leaving liquid phase and solid phase, they are in equilibrium with each other, then the other point, which is that point x1, y1, it will be lying on the equilibrium curve. So, and you are going to get the operating line. The operating line is going to end on the equilibrium curve. So, this point, I'm going to denote that point as point Q. Y coordinate of point Q is y1 and x coordinate of point Q is x1. And the slope of this line is minus ss1 upon ls. Now, if the two phases, they are not in equilibrium with each other, then you will have point Q dash. The operating line will end at point Q dash. When can this happen? This can happen if the two leaving phases, they are not in equilibrium with each other. And if they are in equilibrium with each other, the point Q will represent the other end of the operating line. And in our discussion, we are going to assume that the leaving phases, leaving solid and liquid phases, they are in equilibrium with each other. Now, let us talk about stage number 2. For stage number 2, the operating line, it passes through these points. One point is having coordinates x0, y1, and the other point is having coordinates x2, y2. Capital X0, capital Y1, capital X2, capital Y2. So, the line, the operating line for stage number 2 is going to start at point R. So, if you look at point R has coordinates of x0, y1. So, the operating line for second stage, it starts at point R. And if you look at stage number 2, and if the leaving phases, leaving solid and liquid phases, they are in equilibrium with each other, then the other point on the operating line x2, y2, it is going to end, or it is going to lie on the equilibrium curve. In other words, the operating line is going to end on the equilibrium curve. So you can just see the operating line, it ends on the equilibrium curve. And let me name this point as point T. Point T will have coordinates of y2 and x2. And the slope of this line will be minus ss2 upon ls. And if the leaving phases, leaving solid and liquid phases, they are not in equilibrium with each other, then point T will not come into picture. We will have T dash, which is at which the operating line for the second stage will end. So this point is not lying on the equilibrium curve, and this will happen if the leaving phases, they are not in equilibrium with each other. Let us continue the discussion. Now, if you are dealing with dilute liquid solutions, what you can do, the equilibrium can be described by using the Freundlich adsorption isotherm. So for dilute liquid solutions, the equilibrium is described by Freundlich adsorption isotherm. So in this case, the equilibrium curve, it is represented by an equation of the following form. What is the form of that equation? Capital Y is equal to m into capital X raised to n. So this will be applicable if you are dealing with dilute liquid solutions. So for first stage, now let us learn how to analyze the first stage if you have dilute liquid solutions. So the equation for the operating line for first stage is capital Y1 minus capital Y0 upon capital X1 minus capital X0, that is equal to minus SS1 upon LS. And if you are using pure adsorbent or fresh adsorbent, in that case, capital X0 will be equal to 0. And if you use this in this equation, then it will be capital Y1 minus capital Y0 upon X1, capital X1, that is equal to minus SS1 upon LS. And I'm calling it as equation number 1. Now, the point with coordinates x1, y1, that is point Q on the diagram which I had just shown to you. So, point x1, y1, it lies on the equilibrium curve. And since it lies on the equilibrium curve, it should satisfy the equation of the equilibrium curve. And what is the equation of the equilibrium curve? It is capital Y is equal to m into capital X raised to n. M and n, these are constants. So you have capital Y1 is equal to m into capital X1 raised to n. So that is capital Y1 upon m is equal to capital X1 raised to n. that is capital X1 is equal to capital Y1 upon m raised to 1 by n. And then what I'm going to do, I will use this equation. I will use the equation for X1 in equation number 1. So I will get this equation, capital Y1 minus capital Y0 upon capital Y1 divided by m raised to 1 by n, that is equal to minus SS1 upon ELS. So that is SS1 upon ELS is equal to Y0, capital Y0 minus capital Y1 divided by capital Y1 by m raised to 1 by n. So I have made the negative sign positive by interchanging the positions of Y0 and Y1. And finally, I can get equation for SS1. So SS1 will be equal to LS into capital Y0 minus capital Y1 divided by capital Y1 by m raised to 1 by n. So this equation can be used to find the amount of adsorbent that is required in stage number 1. Let us continue. For stage number 2, for second stage, you have the equation for the operating line, capital Y2 minus capital Y1 divided by capital X2 minus capital X0, that is equal to minus SS2 upon LS. And if you are using pure adsorbent, then X0 will be 0. And if I use in this equation, it will be capital Y2 minus capital Y1 divided by capital X2, that is equal to minus SS2 upon LS. I'm calling it as equation number 2. Now point X2, Y2, that is point T on the equilibrium diagram, it lies on the equilibrium curve because the leaving phases, they are considered to be in equilibrium with each other. So this point should satisfy the equation of the equilibrium curve. So that's why you have this equation, capital Y2 is equal to m into capital X2 raised to n. That is capital Y2 by m is equal to capital X2 raised to n. That is capital X2 is equal to Y2 by m raised to 1 by n. And if I use this equation, or if I use equation for X2 in equation 2, I will get this equation, capital Y2 minus capital Y1 divided by capital Y2 by m raised to 1 by n, that is equal to minus SS2 upon LS. And in the next step, I will get this equation, SS2 by LS is equal to capital Y1 minus capital Y2 divided by capital Y2 by m raised to 1 by n. That will give me an equation for SS2. So SS2 is equal to LS into capital Y2 minus capital Y1 minus capital Y2 divided by capital Y2 by m raised to 1 by n. So this equation can be used to find out the amount of adsorbent that is required in stage number 2. Let us continue the discussion. Now the total amount of adsorbent is the sum of the adsorbent that are required in both the stages. That is SS, the total amount of adsorbent is equal to SS1 plus SS2. We have got equations for SS1 and SS2. Let us use those equations. So SS will be equal to, SS1 is LS into capital Y0 minus capital Y1 divided by capital Y1 by m raised to 1 by n, plus SS2 is LS into capital Y1 minus capital Y2 divided by capital Y2 by m raised to 1 by n. Now let us simplify this. So SS will be equal to LS into capital Y0 minus capital Y1, and over here I am separating the power. So it will be capital Y1 raised to 1 by n divided by m raised to 1 by n. And similarly, the second term plus LS into capital Y1 minus capital Y2 divided by capital Y2 raised to 1 by n divided by m raised to 1 by n. And in the next step, m raised to 1 by n will come as a multiplying factor with LS. So it will be, SS will be equal to m raised to 1 by n into LS into Y0 minus capital Y1 divided by capital Y1 raised to 1 by n plus capital Y1 minus capital Y2 divided by capital Y2 raised to 1 by n. Now in the next step, I will separate the denominator in each term. So it will be, SS will be equal to m raised to 1 by n into LS into Y0 upon capital Y1 raised to 1 by n minus capital Y1 divided by capital Y1 raised to 1 by n plus capital Y1 divided by capital Y2 raised to 1 by n minus capital Y2 divided by capital Y2 raised to 1 by n. So I have separated the denominator. Now in the next step, I will rearrange the equation. So therefore, SS will be equal to m raised to 1 by n into Ls into Y0 in capital Y0 into capital Y1 raised to minus 1 upon n. This term I have brought it in the numerator. Same thing I have done for each term. So minus capital Y1 into capital Y1 raised to minus 1 by n plus capital Y1 into capital Y2 raised to 1 minus 1 by n minus Y2 into Y2 raised to minus 1 by n. In the next step, let us have more simplification. So SS is equal to m raised to 1 by n into Ls into y capital Y0 into capital Y1 raised to 1 minus 1 by n minus capital Y1 raised to 1 minus 1 by n. So I have simplified over here, plus capital Y1 into capital Y2 raised to minus 1 by n minus capital Y2 raised to 1 minus 1 by n. Again simplification over here. Now in the next step, I will do more simplification. So it will be SS is equal to m raised to 1 by n into Ls into capital Y0 into capital Y1 raised to minus 1 by n minus capital Y1 raised to n minus 1 by n, simplification over here, plus capital Y1 into capital Y2 raised to minus 1 by n minus capital Y2 raised to n minus 1 by n, simplification over here. So we got an equation for SS. Now for minimum adsorbent, minimum amount of adsorbent, the differential of equation for SS with respect to capital Y1 is 0. That is dSS by d capital Y1 is equal to 0. Now let us differentiate the equation for SS. So dSS by dy1 will be equal to d by dy1 of the equation for SS. So the equation is m raised to 1 by n into Ls into capital Y0 into capital Y1 raised to minus 1 by n minus capital Y1 raised to n minus 1 by n plus capital Y1 into capital Y2 raised to minus 1 by n minus capital Y2 raised to n minus 1 upon n. Now, in this case, only Y1 is the variable. Rest all other terms, they are considered to be constant. So m is constant, n is constant, Ls is constant, and even capital Y2 is also considered to be constant. So taking this fact into consideration, in the next step, what we will get, dSS by dy1 is equal to m raised to 1 by n into Ls. So now they are out of the differential term as they are constant. So m raised to 1 by n into Ls into d by dy1 of capital Y0 into capital Y1 raised to 1 minus 1 by n minus capital Y1 raised to n minus 1 by n plus capital Y1 into capital Y2 raised to minus 1 by n minus capital Y2 raised to n minus 1 by n. Now in the next step, we will take the differential of each term in the equation. So it is dSS by dy1 is equal to m raised to 1 by n into Ls. Differential of this is minus 1 by n into capital Y0 into capital Y1 raised to minus 1 by n minus 1 minus n minus 1 by n into capital Y1 raised to n minus 1 by n minus 1 plus differential of this term is capital Y2 raised to minus 1 by n, and the last term, which is capital Y2 raised to n minus 1 by n, since Y2 is constant, the differential of this term will be 0. So that's why you don't have that term in this case. So further, we will simplify it. So this is dSS by dy1 is equal to m raised to 1 by n into Ls into minus 1 by n into capital Y0 into capital Y1 raised to, I have simplified over here, I have taken the negative sign common. So it is minus 1 plus n by n minus n minus 1 upon n into Y1 raised, capital Y1 raised to, this I have done simplification over here. So it is capital Y1 raised to n minus 1 minus n upon n plus Y2 raised to minus 1 by n. Let us continue. So previously we got this equation dSS yes by d by 1 is equal to m raised to 1 by n into ls into minus 1 by n into capital Y0 into capital Y1 raised to minus 1 plus n by n minus n minus 1 by n into capital Y1 raised to n minus 1 minus n by n plus capital Y2 raised to minus 1 by n. Now in the next step we will simplify this. So this is dss by dy1 is equal to m raised to 1 by n into ls into minus 1 by n capital Y0 into capital Y1 raised to minus 1 plus n by n minus n minus 1 by n, and now in this case n minus n minus n, n minus 1 minus n becomes minus 1 by n. So that's why you have this term minus n minus 1 by n into capital Y1 raised to minus 1 by n plus capital Y2 raised to minus 1 by n. Then in the next, we know that for minimum total adsorbent, the condition is dss by d by 1 is equal to 0. So let us equate this equation to 0. So it will be 0 is equal to m raised to 1 by n into ls into minus 1 by n into capital Y0 into capital Y1 minus 1 plus n by n minus n minus 1 by n into capital Y1 raised to minus 1 by n plus capital Y2 raised to minus 1 by n. So in the next step, if this term goes to this side, it will become 0 and we'll have this equation. So it is minus 1 by n into capital Y0 into capital Y1 raised to minus 1 plus n by n minus n minus 1 by n into capital Y1 raised to minus 1 by n plus capital Y2 raised to minus 1 by 1 minus 1 by n, that is equal to 0. So previously we got this equation minus 1 by n into capital Y0 into capital Y1 raised to minus 1 plus n upon n minus n minus 1 upon n into capital Y1 raised to minus 1 by n plus capital Y2 raised to minus 1 by n is equal to 0. That is minus 1 by n, I'll rearrange it. So I will bring this term in the denominator. So it will be minus 1 by n into capital Y0 divided by capital Y1 raised to n plus 1 by n. So the negative term becomes positive when it is in the denominator. The second term is minus n minus 1 by n. Again the same thing, divided by capital Y1 raised to 1 by n plus Y2 raised to minus 1 by n. That is equal to 0. Now in the next step, I am going to have a common denominator for all the terms. So it will be minus 1 by n into capital Y2, capital Y0 divided by capital Y1 raised to n plus 1 by n minus n minus 1 upon n into capital Y1 in order to have this term in the denominator of the second term. So I will have to multiply with Y1. So that is what I have done. So it is n minus 1 by n into capital Y1 divided by capital Y1 raised to 1 by n into Y1. So this will result in this term. And then for the third term, I will have to multiply and divide with Y1 raised to n plus 1 by n. So I have done that. So plus capital Y1 raised to n plus 1 by n into capital Y2 raised to minus 1 by n divided by capital Y1 raised to n plus 1 by n, that is equal to 0. Then in the next step, I will have a common denominator, or I will just do one more simplification. So it is minus 1 by n into capital Y0 divided by capital Y1 raised to n plus 1 by n minus n minus 1 by n into capital Y1 divided by capital Y1 raised to n plus 1 by n plus Y1 into Y1 raised to 1 by n. I am separating the power. So it is Y1 raised to 1 by n into Y1 into Y2 raised to minus 1 by n. So I have separated this term, the power. So it is capital Y1 into capital Y1 raised to 1 by n. So this is nothing but capital Y1 raised to n plus 1 by n. Let us continue with this. So we got this term minus 1 by n into capital Y0 divided by capital Y1 raised to n plus 1 by n minus n minus 1 divided by n into capital Y1 divided by capital Y1 raised to n plus 1 by n plus capital Y1 into capital Y1 raised to 1 by n into capital Y2 raised to minus 1 by n divided by capital Y1 raised to n plus 1 by n, that is equal to 0. So in the next step, I will do one more simplification. So this is minus 1 by n into capital Y0 divided by capital Y1 into n plus 1 by n minus n minus 1 by n into capital Y1 divided by capital Y1 raised to n plus 1 by n plus capital Y1, and I will combine this two terms, capital Y1 and capital Y2. So if capital Y2 comes in the denominator, it will become, the power will become positive 1 by n, and then since both the terms have the same power, I can write this equation. So it is plus Y1 into capital Y1 by capital Y2 raised to 1 by n divided by capital Y1 raised to n plus 1 by n, that is equal to 0. So in the next step, I will have the common denominator. So it is minus 1 by n into capital Y0 minus n minus 1 by n into capital Y1 plus capital Y1 into capital Y1 by capital Y2 raised to 1 by n, and in the denominator it will be capital Y1 raised to n plus 1 by n is equal to 0. In the next step, this term will go, if this term goes to this side, it will be 0. So that's why it is minus 1 by n into capital Y0 minus n minus 1 by n into capital Y1 minus plus capital Y1 into capital Y1 by capital Y2 raised to 1 by n, that is equal to 0. So in the next step, I will divide with capital Y1 throughout the equation. So it is minus 1 by n capital Y0 by capital Y1 minus n minus 1 by capital Y1 plus capital Y1 by capital Y2 raised to 1 by n. So I have divided with Y1 throughout the equation. And in the next step, I will simplify this. So it will be capital Y1 by capital Y2 raised to 1 by n minus 1 by n into capital Y0 by capital Y1, that is equal to n minus 1 divided by n. And that is the final equation. The objective was to get this equation. And what is the usefulness of this equation? You can use it to find capital Y1, which is the intermediate concentration. So I hope you have understood the steps that I have used in this derivation. If you have any doubts, you please mention them in the comment section. I will end my discussion for this video lecture. In my next video lecture, I will be discussing one numerical that will tell you how to use this equation. So thanks for watching my video. Do subscribe to my channel. Tell your friends to subscribe to it. Hit the bell icon so that you will be notified as soon as I upload any new video on my YouTube channel. For now, have a nice day. Bye bye. Take care.